Hi, Assalamualaikum warahmatullahi wabarakatuh. In this video, I would like to talk about two examples related to how can you find the result of linear transformation when bases are given. So here we have a transformation function t, you can see it from this, and even though it doesn't tell you what it does, like from what vector space to what vector space, but when you look at this, you can see that this transformation works on changing vector space of with 3 dimension to also vector space with 3 dimension as well, because here the input is 3 and the output here is also 3 dimension. Okay, so that is something that you can get from this what looks like a very limited information, but at least it gives you some idea. And we don't know exactly what t is, but we already know the result, so we know that this is input, and this is input. So here is the image, or I can just call it output. So this is the output, the result of the transformation. This is also output, and this is also output. So what is given here is this is input, and the question is asking to find what's the output. Okay, well, try and study the input given here. You can see the input here is quite special because this is 1 0 0 0 1 0 and 0 0 1. So if you combine them together, so for example, I'm just going to combine these inputs together. So what happened is we can actually write it in a set, and it looks like this: 1 0 0, well, 0 1 0, and 0 0 1. And do you remember what it represents? This is just a combination of them, is just the standard basis. So this is the standard basis. All right, therefore what we can do is, the input given here is this one. So now this is the new input that we need to find what's the output. Before we can find what's the output, we need to be able, okay, in order to do that, the first step here is to write down this input as a linear combination of the inputs given. So that means, can you think of the linear combination of this such that C1 1 0 0 plus C2 0 1 0 plus C3 0 0 1 is equal to this guy 0 3 negative 1. So the first step is to come up with a linear combination of all these vectors here, and that equals to the given input here. Okay, and of course step 2 is to find what are the values of C1, C2, and C3. Notice that this part here, the whole thing here, can be written in this way: 1 0 0 0 1 0 0 0 1. C1, C2, C3 must be equal to 0 3 negative 1. And if you consider the augmented matrix in order to solve for the unknowns C1, C2, C3, this will look like this. And because this is already in the RREF matrix, this is already RREF, we can actually obtain the answers for C1, C2, and C3 straight away, because then it will just be this given input itself. Okay, so based on this, we know that C1 is equal to 0, C2 is 3, C3 is negative 1. We don't have to do any elementary row operations because this is already simplified. And thank God, because we have what we call the standard basis. So we don't need to do anything much, okay? So this is the step 2. The second step, sorry. Okay, right. Next, what we can do is, based on this, we have managed to find what is C1, C2, C3. Therefore, okay, consider this as equation 1. So now let's move on to step 3. Therefore, logically speaking, if I want to find what is the result of giving the input of 0, 3, negative 1 into this function, okay, I want to find what it is. Isn't it the same as having C1 times this, C2 times this, C3 times this is equal to 0, 3, negative 1. So what I'm doing here is I'm just replacing this guy with this whole thing. So this is what's happening in the third step. I'm replacing the given vector here with the linear combination, this one here, with the values of C1, C2, and C3 that we have already managed to find over here in the second step. So here will be 0, and this will be 1, 0, 0. So replacing that, replacing this thing with the linear combination, 3, 0, 1, 0, and plus negative 1, 0, 0, 1. Okay, it makes sense, right? It makes sense since we already know that this is equal to this thing. So we can just substitute this on this, replace this with the whole long expression here. Okay, so this is the new replacement. So here we've just replaced this with this long expression. Then we know that we can consider them separately because we have shown if it is a linear transformation, we know that if we have, for example, 2 vectors, we can do it separately. We can do this separately, u and v. Now here we have 3 vectors. It doesn't matter. It can be generalized to more than 2 vectors. So we can do it separately by having this process here. So 1 part, 2 parts, plus t, negative 1. Okay, so that is the thought process. Yes, based on this idea that linear transformation preserves vector addition and so on. Next is, of course, 0 is a scalar, and we know that if you have t with a scalar right next to a vector, the scalar can be taken out, the constant can be taken out. So we're just going to take out the constant now. Okay, take out all the constant. So here we have 0, t1, 0, 0, plus 3, 0, 1, 0, plus negative 1, 0, 0, 1. Okay, now of course this part here will be cancelled out because you multiply with 0. So what we do next is replace that with the result that we already have. So here the result is already given. Okay, I'm just going to use different color. Well, maybe this one. So this is the result. The result here. So it will be 3 with the result is 1, 3, negative 2 plus negative 1. And the result here also given in the question already. This is the one. 0, negative 2, 2. And we can just simplify the whole thing. 3, 9, negative 6 plus 0 to negative 2, and this is equal to 3, 11, negative 8. So that is the procedure to find the result of the linear transformation when this vector is given and bases are also given here, and this is what we can do. Okay, we have to express the given vector here in terms of the linear combination, find what are the values of C1, C2 and C3 because we need these values. Okay, and then we replace the given vector with the linear transformation that gives us this vector, and we can just proceed as always, as usual. Okay, right. Now, is there an easier method to answer that question? Well, turns out that there is. Okay, there is an easier method. Remember what you have seen in the previous video where you have the standard matrix of linear transformation, and it says right there, if you have vector x, you supply that to a function, it can be easily obtained, the image can be easily obtained if you consider the matrix A and multiply it with the vector that is given here. So we can use that method since what we have here is the standard basis. Okay, these are all the standard basis. Therefore, our matrix A in this case is A is going to be, well, for the first standard basis, this is the first column, so this is 2, 4, negative 1, 2, 4, negative 1. Next is this one, 1, 3, negative 2, and this one here, 0, negative 2 and 2. So this is the standard matrix of linear transformation. And again, what is x bar? X bar in the question here, which is vector x, is 0, 3, negative 1. So this is what we are looking to find, 0, 3, negative 1. Therefore, supply this input right here, and we can just apply this formula, A times with the vector. So this will be 2, 1, 0, 4, 3, negative 2, negative 1, negative 2, 2, 0, 3, negative 1. Okay, and the result here is going to be, well, first row and this column, so this will be 0, 3, so the answer here is 3. For the second column, 0, this is 9, 9 plus 2 is 11, and the last row is 0, negative 6, negative 2, so negative 8, and you see that here we've got the same answer as what's given in this procedure. Yeah, okay, here is the last example for this video, and you can see in this particular example we have a linear transformation defined as T, and here T transforms a vector space in 3 dimensions to another vector space also in 3 dimensions, and here B is a basis for the vector space given here. So here are the bases. Okay, so in other words, these are the input. You can see that this is the output, and output for the second vector here, and this is the output for the third vector, and here is the input, and you want to find what's the result of this when you consider the linear transformation given by t. Now, if I ask you, which method would you be using? Will you be using this method, or will you be using the previous mentioned method here? So I'm giving you a few minutes to think about it. You can pause the video and then maybe after that come back with your own conclusion, and I shall tell you what method should you be using. Okay, right. Well, I assume you have paused the video and you have come up with your own solution or conclusion. So let's see whether your conclusion matches what I'm about to say. Okay, so for this particular example here, there is no easier method. You have to use the method which I have painfully explained in the early part of this video. So you have to use this method, step 1, step 2, and so on. Now, what's the reason why easier method cannot be used? Okay, why can't you use this simple formula to answer this question? Is because the bases given here are not standard bases. Okay, so you have to go back and understand what is the meaning of standard basis. Basically, the standard basis is, well, as you can see here, the difference between the two examples here are the fact that this one are the standard basis. 1, the rest are 0, 1, the rest are 0 at the second component, and for the third component, the rest are zeros. So this is the standard basis, and that's why when you have the standard basis, you can use the easier method, or you can use this procedure as well, this slightly complicated procedure. Okay, now for this example here, you have no choice. You have to apply what I have explained to you just now. So we are going to start off with the first step, which is to think of the linear combination of all this should give you this input here. Alright, therefore we have C1 with the first vector, C2 with 0, negative 1, 2, C3, 1, 0, 1, and it should give you this input 2, 1, 0. Okay, so this is the first step. And the second step is to find the values of C1, C2, and C3, and for that reason you can create the augmented matrix. I'm just going to skip the process altogether. I'm just going to go ahead and come up with the augmented matrix, which is given as such: 0, negative 1, 2, 1, 0, 1. And here is the other side, 2, 1, 0. Okay, and remember what we're looking to find is we're looking to find the value of C1, C2, and C3. Oops. Right, now we're going to apply the elementary row operations, because we need to reduce the matrix to something that is easier for us to calculate, to find the values of C1, C2, and C3. So what I'm going to do is I'm just going to turn this into 0. So I shall consider R2 plus negative 1 R1, and that becomes 1, 0, 1, 2. This one is 1 minus 1, 0, negative 1, 0 minus 1, negative 1, 1 minus 2, negative 1. Okay, also I need to turn this value into 0. I can do it straight away because this line has not been filled up yet. So R3 plus negative 1 R1, 1 minus 1, 0, 2, 0, 2, 1 minus 1, 0, 0 minus 2, negative 2. Right, now I can see that this is looking quite easy. I want to turn this value into 1. Therefore, I can just multiply negative 1 with the second row. That will give me 1, 0, 1, 2, 0, 1, 1, 1. This one is 0, 2, 0, negative 2. Well, what I can do next is I can consider turning this value into 0. So therefore, R3 plus negative 2 R2, and that will give me 1, 0, 1, 2, 0, 1, 1, 1, 0, 0, 0, 2, negative 2, 0, 0, negative 2, negative 2, negative 2, negative 4. And of course, finally, okay, what we can do is we can turn this into 1. So negative 1 over 2 times with the third row, 1, 0, 1, 2, 0, 1, 1, 1, 0, 0, 1, 2. Well, it looks simplified enough for us to try and find the values of C1, C2, and C3. Clearly for this one here, we have C3 is equal to 2. For this one, C2 plus C3 is equal to 1. C2 is just 1 minus C3. 1 minus C3 is negative 1. Okay. And for this one here, C1 plus C3 is equal to 2. C1 is 2 minus C3. C3 is 2, so 2 minus 2 is 0. So these are the values which you can replace right in this position, okay? Therefore, you'll be able to express 210 with the whole long expression here. Okay, and we need this expression because we have some results associated with that, and we can just use the results. Okay, right. Oops. So in the third step, what we can do is third step, we can then find what is the result of the linear transformation of this vector, and this vector is 2, 1, 0. And we can replace this vector with this whole thing here, since we already know what is C1, C2, and C3. Therefore, it becomes, well, C1 is 0 with the first vector, which is 1, 1, 1. You can see it from this one here. Next is C2 is negative 1 with this given vector, 0, negative 1, 2. And then 2 with this here, 1, 0, 1. Okay. And according to what I have explained just now, we can just separate everything here. So we have, and I'm going to take out the constant as well, so just do it straight away. 0 with this guy, oh sorry, okay, 1, 1, 1 plus negative 1 with this 0, negative 1, 2 plus 2, 1, 0, 1. Okay. And the result of this, if you have this input given to the transformation function t, this is the result, this is the output, so we can just replace that. And similarly, if this is the input and we're given that to this transformation function, the result here is this one. So, and finally, if this is the input given to this function, the result is, oh my god, the result is this one. Okay, 1, 1, 0. Okay, and therefore I'm just going to substitute all the results here, and I don't have space and I need to erase. some parts. All right, so continuation from step 3. Okay. So here we have therefore t. Okay, we want to know what's the answer to this. This is equal to, well, this one is cancelled out because you multiply that with 0, it's gone. Then -1 with the result here. The result is given as -3 to -1. So -3 to -1, and then this one here 2, and the result for that is 110. So 110, and you can simplify that. It becomes, well, +3 plus 2 is 5, -2 plus 2 0, +1 0, so +1. Okay, so this is the answer, and thank you very much for watching, and I'll see you in the next video.